Hello, everyone. Welcome to this talk. Today, we'll be talking about scale testing the network control plane. In particular, talking about a benchmark that HashiCorp did earlier this year on a service networking project, HashiCorp Consul. So a bit about myself. My name is Mishra. I'm the advisor to the CTO at HashiCorp. So I work in the office of the CTO on strategic initiatives, both internally with internal teams and externally with our partners. I also lead a product incubations team. I went to school for computer engineering. I worked as a software engineer, also as an operations engineer, so kind of understand both sides of the software delivery process. I empathize with both developers and operators. I love open source, and here's the few kind of projects I've worked on. Atlantis, virtual kubelet project as a provider maintainer for the Nomad provider, on CDK for Terraform, on Dapper, which is a project by Microsoft, which is a distributed application runtime. Also worked on HashiCorp Waypoint, which is a tool to deploy to various platforms, so you can check them out. All right, so a bit about what we're going to talk about today. Agenda is pretty straightforward. We'll talk about some of HashiCorp's history with benchmarks, talk about scale testing Consul in the Consul Global Scale Benchmark. This is the benchmark that we did earlier this year. So we'll discuss the results, the benchmark setup, how we use Datadog and everything, and some of the multi-platform testing we did with it. And then we'll kind of conclude the doc with thanking the partners and also some of the useful links like the report that we published about the benchmark and also the GitHub repo that has all the configuration in it and the link to it essentially. So a bit about HashiCorp benchmark. So we did our first, benchmark, a public benchmark that we published in 2016 on HashiCorp Nomad, which is a cluster scheduler. So we spun up 1 million containers in 5 minutes on 5,000 hosts on the Google Cloud platform, essentially. And then we redid the same style of experiment again, but this time with 2 million containers. It took about 22 minutes. This had nodes spread across 10 different AWS regions with 6,100 hosts, and this was all on AWS. So for Consul, which is a service networking project, we wanted to do an experiment of this scale with like thousands of nodes and many services in the cluster and kind of match to it. And this is where the Consul Global Scale Benchmark comes in. All right, we're going to start off talking about the benchmark results, and then we're going to backtrace from there essentially. So we did the Consul Global Scale Benchmark and released the results in April 2021. We did the benchmark in February. So what we did here is kind of spun up 10,000 nodes on AWS, on EC2 in one AWS region. And we kind of spread applications across these hosts and just containers, I guess, in this case. And what we wanted to measure here is kind of propagation time for a change. So let's say we were to change an endpoint, essentially register a service or deregister service. How quickly does it, what time does it take to kind of propagate that change from the control plane all the way down to all of these applications that are running on these hosts, essentially. So what we noticed is it took about a second for the kind of the propagation time for a change to propagate to about 172,000 plus containers, and which is really, really impressive. And this is all powered using 5 Consul servers, which were the control plane for this mesh. And this is kind of the graph that showcases the propagation time for a service deregistration event. So on the x-axis, you'll notice the time is in milliseconds. Y-axis, you see the number of service instances kind of, receiving or seeing the event. And you can also see kind of the latency distribution all the way from P50 to P99. All right, the second test we did was the intention propagation. So intentions are ways we define access permissions and policies around traffic shaping in Consul. So essentially, what service is allowed to talk to what service. So here what we did is kind of changed an intention, and we saw about 900 milliseconds of propagation time from the control plane all the way down to 9996 hosts. And this is the kind of the intention propagation time graph where you see the time again is in milliseconds on the x-axis. The y-axis, you see number of nodes this time. So this was measured at the Consul agent level. So what you'll notice here is there's 9996 nodes and 4 nodes are missing. And those 4 nodes are essentially may or may not be running any workload, maybe running workload that wasn't relevant to this change. Again, you can kind of see the latency distribution here. All right, let's talk about the benchmark setup. So we had a pretty straightforward benchmark setup. We had 5 Consul servers that created the Consul control plane. There were 36 vCPUs, 72 gigs of memory spread across 3 AZs. We had 3 Nomad servers, which was a scheduler, which is 16 vCPUs, 128 gigs of memory spread across 3 AZs. Again, 10,000 Nomad clients essentially running these are running the applications on containers. And these were 4 vCPUs and 8 gigs each. And we had, again, spread across 3 AZs. We had 2 autoscaling groups of 5,000 nodes each that made up the 10,000 nodes. And then we had about 100 load generators, which were 2 vCPUs, 4 gigs of memory. These were just to test whether the service mesh was configured correctly. These were spread across 3 AZs again. And we used Slow Cooker for our load generation, which is a project by Buoyant, the service mesh company. And all of this was kind of running in US East 1. We wanted to just use one region. Cost was a big kind of factor in this, and we wanted to make sure we are kind of keeping our cost in control as well. We had a limited amount of credits. So we couldn't do multi-region in this case. And we just wanted to test the control plane side of this. And I think being in one region was good enough for this one particular experiment. All right, talking about the benchmark workload. So we wanted to mimic a more kind of, real microservices like environment. So we did a 3-tier service architecture. We had service A, service B, and service C. So service A is dependent on service B, which is dependent on service C. And then if someone were to call out to service A, it would talk to service B, then call out to service C. You get a kind of combined response back. And these responses were just text essentially. So we had 3 tiers of these kind of services. So we had 1,000 unique services per tier, and a total up to 178,000 total service instances, containers that were running for this experiment. Now, this does not include the sidecar proxy. So if you include the sidecar proxy, this comes up to 356,000 total service instances with Envoy as a sidecar proxy here. Scaling up all of the kind of the infrastructure, we use Terraform to bootstrap the infrastructure and the workloads. I'll be leaving a link to the GitHub repository that has the Terraform configuration. So if you want to try this out, you can try this out. So essentially the network resources, VPC subnets, a console control plane, Nomad servers, these were all kind of done, set up using the Terraform, and also submitted all the jobs to Nomad and queued them up. We wanted to make sure that we use, as soon as the nodes come online, we kind of scheduled workloads on them. Again, the cost was a big factor. So this was, important here. And the one thing here is that to note here is that each node had a random delay when it would boot up. So it would choose a number between 0 and 26 minutes, and then it would wait for that time before booting up. And this was to make sure that, we don't overload the system. We gracefully kind of scale up. The probability of success for running a test is higher each time because, we can't run like 10,000 nodes all the time. Again, cost is a big factor here. So that essentially that delay would help us kind of gradually scale up the system because Nomad is able to schedule really quickly, as you saw earlier in the benchmark results that I talked about early on in the presentation here. All right, now talk about kind of the Datadog configuration. Pretty straightforward Datadog configuration. We had a Datadog agent. All we did is enable the console check in this case, allow the Datadog agent to read journal D logs, configure the Datadog agent to read logs from the console service, enable the journal D logs shipping via Datadog agent, and then restart the agent. And this was on the control plane, which were the console servers. So here's a snapshot of the cloud init data for the console servers. So as you can see, we're just like moving a file to enable the console check, then allowing Datadog agent to access journal D, then enable journal D logs for console. The console service enable log shipping via Datadog as well, and then restart the agent. Pretty straightforward configuration here. So for the Nomad server, which is a scheduler, all we did is kind of enable the console check for the console agent running on the Nomad server, and then the console check for the Datadog agent, and then we restarted the Datadog agent. And this is the snapshot of the configuration. Pretty straightforward. All we're doing is moving a file and then restarting Datadog to do this. All right. Now talking about the Nomad client, and this will have a lot of interesting steps, and that's just because it was actually running the workload, the containers, using Docker, and then running the console agent as well on it. And and so on. So what we did is kind of enable the Datadog check for Datadog agent, enable the console check for the Datadog agent, allowed Datadog agent to access Docker, allowed Datadog agent to read journal logs, enable Docker logging via the Datadog agent, and then configure Datadog agent to read logs for Consul and Nomad services, which are the processes running on the system, and then restart the Datadog agent. Here's the configuration for the Nomad client and the kind of the Datadog configuration for the Nomad client here. So yeah, this one's a little bit more involved. It has a few different things. So we are kind of enabling log shipping and so on, and also enabling like the Docker listener in this case. But what's interesting is we're using processing rules to exclude some logs to go to Datadog. And this is just because we're producing a lot of logs. Some of these processes are running with the log level debug or maybe a little bit higher than info. So we were generating a lot of logs. So we just wanted to kind of send logs that were useful to us up. And we just used exclude at match filter, exclude at match processing rule to do this. And then you'll also notice we're using tags, which essentially we're tagging these logs that are being shipped up to Datadog so we can filter them later on, maybe based on, like, let's say in this case, internal IP address or external IP address that Amazon has given us. We can trace things from the control plane and to the nodes that are running kind of the data plane side of things here. We're also like kind of tagging it with like console_server_shuffle, which is just a internal flag, an internal flag that we kind of essentially wanted to note. All right, so there were, there was a gotcha here. So what we noticed is that, at some point we didn't see logs coming into Datadog, and we were like, we are like missing some logs here. And so what we ran into is that we were producing a lot of logs, and so our syslog rate limit, which was, I guess, set to whatever the default rate limit is. So essentially we were being rate limited at this point. And so what we thought was it was a Datadog agent not shipping logs, but it was actually our syslog. And all we did is kind of change that rate limit and removed that rate limit from it. And this is kind of some of the code that you can use to kind of remove the rate limiting. But an interesting thing that we noticed, if you produce too many logs, there are system things that can kind of prohibit you to kind of send all the logs up here to Datadog. All right, the scaling up side of things, pretty straightforward. Here's some of the graph that we generated from Datadog, and these are just kind of prettified with the console color scheme here. So it took about 51 minutes to bring up all of the 10,000 nodes with all of the workloads scheduled on them. And this took a little bit of time just because of that random delay that I talked about, the delay that the nodes would choose from 0 to 26 minutes or so. And this is very interesting. You can see like there's like 10,000 nodes. There's about like 6K or so services, console services, and about 300K plus service instances that are running in the cluster, which is pretty interesting. And the CPU usage was about 40% or so, maybe 41 to 45% or so in the beginning when everything was scaling up, and then it kind of stays consistent throughout when everything is online, which is just a glimpse into how the control plane, the CPU usage is like. Right, and not only did we test this on EC2 instances, but we also wanted to try kind of the I guess EC2 instances running Nomad. We also wanted to try it for Kubernetes. And so we ran a 500 node Kubernetes cluster, which we did like kind of the endpoint propagation time test here. So you can see took about 700 milliseconds for 1990 service instances to kind of get the endpoint propagation event. And you can see the graph on the right, very similar graph that you saw earlier. Time is in milliseconds in the x-axis, number of service instances on the y-axis. And then you can see the graph on the left, which is the total number of running pods. And this was kind of generated using the Datadog dashboard for Kubernetes. All right, the Kubernetes configuration, again, very, very straightforward. On the left, you see the Helm values that we provided the Helm chart for Datadog agent. We enabled statst, we provide the API key, we enabled APM, we enabled logs to be shipped for our containers. And then we set some environment variables to exclude some of the logs to be shipped up there, again, to kind of make sure we don't send logs that we might not need for the experiment. On the right, you see a Kubernetes service that we created to ship stats D, data to the Datadog agents, and this is to kind of send some of the stats D data that might be coming from some applications to the Datadog stats D port. All right. In conclusion, we actually didn't do anything sophisticated, or didn't try to do any performance tuning on the Datadog agents themselves. So pretty much using the default settings and in the docs that are out there for Datadog, and which is very impressive for a benchmark of this magnitude. There was no performance tuning that was needed for the Datadog agent to perform it, and they did pretty well here. All right, in terms of the data collection, we collected a decent amount of data. So we had stats D data from Consul, Nomad, Envoy, proxies, Kubernetes, load generator instances. We had logs from Consul, Nomad, Envoy proxies, the fake service application, the application that was scheduled, and the application that was in that kind of 3-tier service architecture. We had APM data to generate service-to-service traces and generate latency graphs. And then so Datadog processed around 1.8 billion log events from the beginning of our us working on this experiment with hundreds of nodes all the way up to 10,000 nodes here, which is pretty impressive. So again, with this, I would like to thank our partners, AWS and Datadog, for partnering with us and providing us with credits to perform the benchmark. And then, if you want to read the detailed report about this, you can go to HashiCorp.com/CGSB, which stands for Consul Global Scale Benchmark. And there's a full detailed report about it. I couldn't touch all of the portions of this report in this talk, but you can read it if you like. And then there's also the benchmark configuration, the Terraform configuration for this benchmark. So you can visit github.com/HashiCorp/console-global-scale-benchmark to access this as well. With this, thank you so much. Thanks for spending some time watching this talk, and have a good and amazing dash.